Thank you very much, Tuhin. It's a great pleasure to be here. Thanks for the invitation to this school. My first time in Bangalore, and in particular in this beautiful institute. So I was originally asked to give lectures on soft collinear effective theory. I will also give some lectures on heavy quark effective theory. And it's very natural, actually, because as you'll see, we'll use heavy quark effective theory as a warm-up to soft collinear effective theory. The language that we're going to use is actually quite similar. So I will always upload loads of my lecture online before the lecture starts, so you can take a look there, or also take a look afterwards. And then, of course, as I understand, we have the discussion sessions later in the day to address questions and maybe even do some exercises together. So, you know, you heard already quite a lot this week. You had an introduction from Manish, I understand, 2 lectures on sort of the very basic principles of effective field theories. And then HQET is a particularly interesting example of an effective low energy field theory. And of course, dispersion relations is not directly based on a particular EFT, but is a technology that can be used in the context of all field theories, including effective field theories. So let me start this course with a motivation. So the course is on HQET and soft collinear effective theory. And of course, the motivation is straightforward. Why do we do effective field theories? Why we do effective field theories? Because typically in science, and in particular in physics, we deal with problems containing several distance scales. Now, with scales, you can think of really distance scales, and then this would be large scales like the size of the solar system, and this would be small scales like whatever subatomic scales. You can also invert the scale and think in terms of energy, which is usually what we do in particle physics, and then going up here meaning very high energies, which typically corresponds to exploring small distance scales, and going down here means low energies and larger distance scales, okay? And just, you know, let's just think of something at the LHC, let's say Higgs production at the LHC, okay? So what do we do at the LHC? We collide 2 protons. Protons have a mass of a GeV, roughly. So this sets one scale. Let me put it here, for example, proton mass. So a GeV. We know that protons consist of quarks and gluons. They have some substructure. The scale for this substructure usually we call lambda QCD. So here we talk about, let's say, hundreds of MeVs. But then we want to produce a Higgs boson, which has a mass of 125 GeV, so 100 GeV, okay? And then actually, to produce a Higgs boson, the most efficient mechanism is to fuse 2 gluons and produce a top quark loop. So there's also a top quark up here. The top quark has a mass of roughly 175 GeV, okay? But then inside the loop, we can also have B quarks running instead of the top quark. So there's also a B quark relevant with a mass of 5 GeV. Okay, so you already see the general picture. You're never in a situation where you just deal with one number, one scale. It's always going to be a multi-scale problem. And of course, if you do chemistry or biology, this is even more true, of course. Physics is already the most fundamental science that we can do. So, you know, you can say, well, what's the problem? I know the standard model, I just compute this, but if you sit down and do that, you will find it's very hard for many reasons, for technical reasons, but also for conceptual reasons. So basically, think of EFT as a way of simplifying such problems. That's it, basically. An EFT disentangles scales. It will deal with these problems one at a time. We'll typically start with the highest scale, and what we do at the technical level, we say we integrate out very short distance physics. We imagine we zoom out with our lenses. We don't look at the most smaller structure, we look at larger structure, yet larger structures, and then we can sort of integrate out this very short distance physics and obtain a description of the long distance physics that is simpler because it has fewer degrees of freedom, fewer scales. So that's why we do EFTs, okay? You can also think of EFTs as something like a Taylor expansion in the context of quantum field theory. Taylor expansion, usually you have a function depending on several variables. Maybe one variable is much bigger than the other. You can expand in the ratio of the two, okay? This is what we would like to do. So basically, we can reduce multi-scale problems to a sequence of single-scale problems. And in the simplest problems, this is just for technical simplification. So for instance, when people do multi-loop calculations, the frontier of the field is typically 2-loop or 3-loop, depending on how many scales the loop function depends on. And very many times, when a loop function depends on 2 or more masses, what people do when they want to do multi-loop calculation is they do a Taylor expansion in the ratio of the masses, even if that ratio is not particularly small, let's say a half. They just compute the first 50 terms in the Taylor expansion. Then even a half becomes a good expansion parameter. As soon as you expand, you have one parameter less, and the integral class becomes much simpler. So this technique is actually used in practical loop calculations, even though all people want to do is to compute a loop function depending on several variables. Nevertheless, they use EFT technology to expand and simplify the problem. But the problem is much more fundamental in QCD or other strongly coupled theories, because this is also the formalism to separate what you can calculate from what you cannot easily calculate. So in the context of QCD, we know that up here, at very high energies, we have asymptotic freedom, and we can perturbatively compute how top quarks interact with gluons and Higgs bosons. But down here, we have confinement, okay? Which means that the degrees of freedom of the theory are not the degrees of freedom that we use to construct the standard model. In the standard model, we have quarks and gluons. In the real world, we have protons, and pions, kaons were mentioned in the last lecture this morning. So I cannot use my perturbative standard model to go all the way down here. So what do I do in practice? I draw a line somewhere between the non-perturbative and the perturbative region. This line is usually called mu, some scale that you throw in by hand. And everything above mu, we try to describe using perturbation theory. Everything below mu, we have to parameterize and get, typically in the best case, get from experiment or get from, let's say, lattice QCD. And you all know that if you were to compute the Higgs cross-section, at the end of the day, you use something called parton distribution functions. Okay, what are parton distribution functions? Well, they tell you the probability to find a quark or a gluon of a certain momentum fraction inside the proton. And then what you really compute is for instance, for gluon fusion, is a gluon to Higgs cross-section convoluted with gluon momentum distribution functions. And these are non-perturbative. Okay, you extract them from data. And in order to do that step, factorizing calculable from non-calculable or short distance from long distance, we need EFTs. Because at a technical level, we integrate out everything above the scale mu. Perturbatively, we compute these things. And then below the scale mu, we match it onto a low energy effective theory, which in this case is called parton distribution functions. Okay, we don't call it low energy effective theory, but actually parton distribution function at the deep of the heart are matrix elements defined in soft collinear effective theory at the end of the day. Okay, so factorization is much more profound, the much more profound notion here. We want to factorize long distance from short distance physics, which is, you know, which is absolutely essential when the low energy degrees of freedom are different from the high energy degrees of freedom. Now, my factorization theorem will basically describe everything below mu in terms of functions that I take from experiment or from the lattice, let's say, the Patron distribution functions. So I cannot, if I try to go with low into the non-perturbative region, my perturbation theory breaks down, but I'm not forced to do that. It's simply important that I can draw this line, that I can handle everything that is above, compute everything here, and then the only thing I need is, from the low energy theory, some basic matrix elements like the Patron distribution function. And you see, this is a very profound statement. We can have situations where the low energy effective theory needs to be formulated in terms of different degrees of freedom than the fundamental high energy theory. And in fact, the Karl Lagrangian, the lectures that Anish gives, is a beautiful example of that, because pions are bound states of quarks and gluons, pions and kaons, etas, right? These are the right low energy degrees of freedom of QCD below a GeV. This is the light particles that you can generate, but it's not quarks and gluons, it's pions, okay? So you somehow have to connect the quark-gluon world of the standard model to the pion language of Chi-PT. And without an EFT, there would be no consistent way of doing this. So this is really, you know, this is why you need to learn about EFTs, because at the end of the day, everything we do is EFTs. In some way or another, it's everything you do in research is linked to EFTs. Now, why in particular soft collinear effective theory? Soft collinear effective theory, so SCET, is the effective theory for high energy processes of light particles. High energy processes, let's say, involving light particles. Why should this be interesting to you? Well, that's what the LHC does. You take the most powerful accelerator on the planet, you smash together two protons, you produce, we don't know what, maybe dark matter, maybe SUSY particles, Higgses, Z bosons, lots of heavy stuff. But at the end of the day, they decay, and in the detector, you see again pions and kaons, okay, which is essentially almost massless particles with very high energy. The key here is the high energy. Energies of order multiple TeV, because we have 14 TeV collision energy, 13. And this collision energy goes into the kinetic energy of the final state particles. Now, what is a light particle with very high energy? So let's say a pion at a TeV, how should you think of this? Anyone remembers the pion mass, roughly? I already wrote it down, but 140 MeV, right? So let's say 100 MeV to make it simple. And now I'm talking about a TeV energy. So a TeV is 1,000 GeV is 10,000 times the pion mass. So you have a pion with an energy that is 10,000 times its mass. Well, that means this particle, to a very good approximation, is massless. If you were to describe it as a massless particle, you wouldn't make a big mistake, okay? So, you know, this is like a light particle, like a photon. These are things traveling at the speed of light and moving like light particles. So if we measure their space-time trajectories, they're very near the light cone. So we'll see that this is the main challenge here. We want to do an effective theory near the light cone. This is why, on the one hand, this SCET is very powerful because it is the effective theory for high energy physics at particle colliders. But it's also one of the most complicated EFTs ever developed. It's full of subtleties. It's a subject that is over 20 years old now, and people are still surprised by this theory. Every time you try to do something complicated new, you find new tweaks to the theory, unexpected tweaks often. And that's also what keeps the field very, very interesting and very exciting. Actually, originally, SCET was not developed for the LHC, was developed in the context of B physics. B physics with a capital B. What's B physics? Well, the capital B, do you know what the capital B meson is? Right, it's a bound state of a heavy quark, the bottom quark, with a light quark down or up or strange. And we had factories, we had experimental facilities producing these B mesons and anti-B mesons, and then you could watch these particles decay. And of course, the decays of these particles are interesting because they happen through the weak interactions. The heavy B quark of the standard model can decay to lighter up or charm quarks. And then we can have weak decays, flavor change, so-called flavor changing processes, measuring the structure of the Gabibo-Kobayashi-Mascawa matrix, CP violation, which is a phenomenon in this matrix, and so on and so forth. So this was a very, well, still is a very interesting field, very lively field of particle physics. Nowadays, this is done in the LHCb experiment at CERN, but also in the Bell 2 experiment in Japan. And in these B factories, one measured decays of B mesons. So, for example, I could have a B meson decaying to a pion. So let me make this concrete. Let's say a B minus meson decaying to a neutral pion, a muon, and a neutrino. And at the quark level, this would be a decay where we have a B quark and an anti-U quark decaying to a U quark and an anti-U quark. That's the neutral pion plus a muon plus a neutrino. And you see that basically here we have the transition of a B quark to a U quark. So for instance, people studied these kind of processes to measure the matrix element VUB of the CKM matrix, which has an imaginary part that mediates CP violation, etc. But you also see what the problem is. You're dealing with mesons here, so you have to somehow be able to describe the binding of the quarks inside the mesons. Okay? And there were these so-called exclusive decays. There were also inclusive decays where you would have a B decaying, for example, to any hadronic final state containing this up quark plus a muon, neutrino, or charm quark here. Or there were things like B to hadronic final state with a strange quark plus a photon. So there was a long variety of decays that were measured and people wanted to calculate. And there were also things without any leptons in the final state. So things like B to pi pi or pi k, completely hadronic decays, okay? And for these various decays, various technologies had been developed. In particular, this is one where Anish and collaborators worked a lot, these so-called inclusive decays, semi-leptonic or non-leptonic, where you could use effective theories, basically this heavy quark effective theory and variants of it, to do sort of model-independent calculations of these hadronic physics that is there because of these bound states. And in the case where this was completely non-leptonic here, with our own group, a long time ago, we developed a formalism called QCD factorization, which was also based on the heavy quark expansion. And then basically, I believe SCET was an attempt to understand this factorization in the language of effective field theory. This is how it started. It started in B physics. But actually then very soon people discovered, well, actually we can also use this at the LHC because actually we'll have even higher energies there. In B decays, the energies are 5 GeV, typically the mass of the B meson. Here the energies can be up to TeV, right? So in a way nowadays, SCT is mostly applied in the context of high energy collider physics, but also dense QCD matter. So people studied jets in a quark-gluon plasma. It's used in hadron physics to study form factors. It's used to study properties of scattering amplitudes in QCD, but also in supersymmetric Young-Mills theories. And it's also used in the context of beyond the standard model physics. And there's an annual conference on soft collinear effective theory since 2003, where people meet to report the recent progress in the field. So it is still a very, very lively field. Now, we'll see both in heavy quark effective theory and in soft collinear effective theory that they are a bit, how should I say, unconventional, more complicated, I already mentioned, for a reason that basically maybe is clear at the end of my lectures. In both cases, well, in the cases Anish discussed yesterday, sort of the standard construction of effective field theories, what you have in mind is that at high energies, there are some heavy particles around, the top quark, the Higgs boson. If you live at low energies, you don't see these particles, maybe you don't even know that they exist. So there has to be a way of describing the effects of these particles in terms of the couplings of operators in an effective low energy Lagrangian. So in that sense, we can really integrate out these heavy new particles, the ones we know and the ones we don't yet know. So the parameters in the standard model, the fine structure constant or the Higgs self-coupling, they may contain physics of yet unknown heavy particles, which one day, if we discover them, we'll discover the relation, how, say, the lambda coupling of the Higgs depends on the value of the masses and couplings of these new heavy particles. But in that situation, heavy particles can really be integrated out in the sense that at low energy, you don't need to know about their existence. In the cases we will discover here, that is not the case. So for instance, at the LHC, if I have a collider where I collide protons at 13 TeV, the high scale clearly is 13 TeV, but it's not that I can integrate out this scale. I can remove it completely from the low energy theory because my particles in the detector, they will carry a fraction of that large energy. So somehow it is at the same time the short distance scale in which I want to expand, but it's a scale that is imprinted in the kinematics in the low energy theory. And likewise here in B decays, I cannot integrate out the B meson or the B quark because I want to study decays of that B meson. So it's more that the large mass of these objects enters the low energy theory in the form of the energy of the particles. And that's more than a small complication. So the standard EFTs, let me just call them standard EFTs, they are based on the Wilsonian operator product expansion, OPE, operator product expansion, and that's basically, that works in Euclidean space, where really short distance really means if I look at the typical separation between two fields, let's say connected by the exchange of a new heavy particle, the typical separation delta x really goes like 1 over the mass of that particle and really in some sense goes to 0. So it's really a short distance expansion. On the other hand, SCET and also HQET, it's in some sense a Minkowskian generalization. And what that means, that let's say if I have two particles, x1 and x2, you know, if those are 2 points connected by a propagator of a very new heavy particle, then the distances are very nearby of order 1 over m. But in a Minkowskian situation, I have that the distance of these 2 points is approximately 0, but the separation of the points is not 0. So for instance, if I look at a particular x1 mu, x2 mu, this can be much bigger than 0. And I mentioned already earlier, what is a pion at a TeV? Well, it's a light-like particle, so it travels along a light cone. Points upon a light cone have x squared equals 0, but x is not 0. The two particles can be arbitrarily far apart and still be connected by a light-like distance. So this is light-like, but not point-like. And in that sense, this will be intrinsically a non-local theory. So these effective theories are non-local. Everything will be non-local. And not non-local in a minimal sense, non-local in a large distance sense. But always light-like separated. And there is no operator product expansion that could be the basis of this. So these theories are really based on a different notion, and that's called the method of region. And we'll discuss this starting tomorrow at a very basic level. So just to give you a picture why, you know, this is not just another EFT like all the other EFTs. This is really something more different. More special, but it's what is needed to have an effective theory for high energy processes. So let's do heavy quark effective theory for the rest of today. Heavy quark effective theory is an effective theory describing the properties of bound states of a heavy quark Q with light degrees of freedom. And degree of freedom here sounds fancy. It really just means quarks, antiquarks, and gluons. Now, when we say heavy quark, light quark, what do we mean actually? How would you define a light quark, like the ones Anish was discussing in his lecture? When would you call a quark a light quark? It has to be light relative to something. What's the something? Lambda QCD. Yes, speak up, don't be shy. I still have a cold. My hearing is not very good. Lambda QCD, precisely right. So QCD gives us a scale. It has its own dynamically generated scale, which separates things into light and heavy relative to lambda QCD. Lambda QCD doesn't have a very well-defined meaning. You could say it's roughly a third of the mass of the proton, because a proton consists of 3 constituent quarks, we call these things. So then it's 330 MeV. You can also say it's the scale at which the running coupling alpha S becomes of order 1. That happens to be at a scale around that, whatever, half a GeV or so. Okay, so lambda QCD, a couple of hundred MeV. So which quarks are light quarks then? Up I heard, down I heard, strange I heard. More offers? No, good. Up and down, surely, excellent, right? Because their masses are whatever, 2 or 3 or 4 MeV, much, much lighter than lambda QCD. Strange is a bit borderline, 100 MeV, it's the strange quark mass. It's about a third of lambda QCD or so. So the strange is usually included in the light quarks. Then we have an SU3 symmetry of the light quarks, and then the chiral Lagrangian is based on that. And what are the heavy quarks then? So certainly top and bottom is excellent, right? Because the bottom with 5 GeV is still at least 10 times heavier than lambda QCD. The top is way much heavier. Charm, again, charm is a little bit like the strange quark for the light quarks. Charm has a mass around whatever 1.2 GeV, so it's maybe 3 or 4 times lambda QCD. It's a heavy quark, but not too far away from lambda QCD. And the top would be wonderful if it had bound states, if it formed mesons that we could produce in an accelerator and then watch them decay. Unfortunately, the top doesn't do that. The top decays too fast. The time it takes to build a hadronic bound state is of inverse order lambda QCD, but the top decay rate into bottom plus W is faster. So that's why we're stuck with B mesons. And that's why Q here is typically a B quark or a charm quark. But that's only because nature didn't give us more useful heavy quarks. And of course, it's really a simple 2-scale problem where we just consider the mass of this quark to be much, much heavier than lambda QCD. And we want, in some sense, we call this scale the hard scale, even though high would be more reasonable a name. And this we usually call the soft scale, even though low would be a better name. But somehow when we talk about soft QCD physics, we usually mean things that live at the scale lambda QCD, and hard QCD processes are short distance processes which happen at much higher energies, much smaller distances. So we want an effective theory describing the properties of bound states of that type. You could also have bound states of a heavy quark with a heavy antiquark, for example. This is, for instance, the charmonium or bottomonium states. They're also meson states. And there's also an effective theory for them. But interestingly, it's not exactly heavy quark effective theory. It's called non-relativistic QCD. The names are completely different. The theories are much more similar to each other, but not completely identical. It's the power counting that is a bit different. In fact, the effective Lagrangian is in some sense the same, but what you count leading order and next to leading order is different in the two cases. So I'll focus on this case for the purposes of these lectures. And it's clear that this is not going to be a theory in which we simply integrate out this heavy quark, because then it's gone. But we want to understand the properties of, let's say, a B meson versus a lambda B baryon versus an excited B meson. So we cannot integrate out that scale altogether. So it's actually a good question. What is there to integrate out? How can we simplify the construction of this theory with respect to simply QCD? And we'll see that in this limit, MQ much bigger than lambda, new symmetries arise, so-called heavy quark symmetries. And these symmetries are not manifest in QCD. So it is useful to construct this heavy quark effective theory because it is an effective theory built around this symmetry limit. That's why it's useful. And then these symmetries are broken by corrections of order 1 over MQ. What's the picture that you should have in mind when you think of heavy quark effective theory? The picture is very simple. Picture is this. This is the heavy quark. And this is the other stuff. Now, of course, you can call this antiquark, but you all know it's more than that, right? I mean, it has the flavor quantum numbers of an antiquark, but then there are gluons binding these things together. And if we have gluons, gluons can create little quark-antiquark pairs, etc. So there's lots of stuff inside here. Sometimes it's derogatively called the brown muck. I don't like that name particularly, but just to make it clear that there's no perturbative description of what this stuff is that partners up with a heavy quark to make a B meson. We know it's a single heavy quark. If there would be two heavy quarks, it would be heavier. Why do I draw the heavy quark as a small circle here and not the big circle since it's so much heavier? Well, the thing is that this is a very heavy quark. We want to take the fictitious limit where its mass becomes infinitely heavy. So we can consider the limit lambda over m to 0, so m to infinity. And if a quark has infinite mass, if it's stuck, it's stuck. I mean, if it moves, it moves. If it's stuck, it's stuck, but you can't change its motion. So if I go to the rest frame, this thing just sits there, and the light stuff somehow orbits around it. Okay? And of course, these are point-like quarks, so it has no spatial extension. If you wanted to associate a scale with it, it would be the Compton wavelengths, which would be 1 over m. And m goes to infinity. So that's why I draw this as a small circle here. The size of this brown MAC is not 0. It's roughly the inverse of lambda QCD, right? The typical size of hadronic bound states. The inverse of lambda QCD, or a femtometer. Femtometer is an inverse of 200 MeV. And then the heavy quark is a fermion. It has a spin. So let me draw a spin here. But the spin really interacts with the other particles in the form of a magnetic moment. And the magnetic moment again scales with the mass, 1 over m. So the magnetic moment also goes to 0. So that's why I drew a very small spin, because this interaction goes to 0 in the limit where the mass goes to infinity. So that's the picture, basically. Now, how can we make sense? How can we take this picture and make something useful out of it? Well, once you know the answer, it's incredibly simple. So the key element here is what I said earlier, that this is an infinitely heavy quark. It just sits there, or if it moves, it just moves. You cannot easily change its motion. Okay, so let me assign a 4 velocity to the meson. 4 velocity is a vector v mu. It's a 4 vector such that v squared equals to 1. And this is the 4 velocity for the whole meson. And of course, I can immediately go to the rest frame. And in the rest frame, simply the spatial components of this 4 velocity vanish. And then this relation means that the time component is simply 1. Okay, so this is a 4 vector, which in the rest frame is 1, 0, 0, 0. And if you boost to another frame, it's some vector that squares to 1. And now we write the momentum of the heavy quark in the following way. We say, well, this heavy quark basically defines what is the rest frame of this meson. If the meson moves as a whole, the heavy quark will move with the same velocity, to a very good approximation. So we write this p mu as mq times v mu, the meson velocity, this guy here. But now the quark velocity and the meson velocity, maybe there's a small difference because of all this other stuff around it which interacts with the heavy quark, right? So think of this brown Mach as whatever, some very light stuff that is trying to kick this very heavy quark that just moves along. So there's going to be some momentum exchange, k, but the components of k are much, much smaller than mq. In fact, the components of k are typically of order lambda QCD. So this is called the residual momentum. And this residual momentum is from the soft physics, from the soft interactions between the heavy quark and the light degrees of freedom. This is a triviality, basically. I'm just splitting up this momentum. I'm saying, well, the overwhelming contribution to the heavy quark momentum is the trivial part that simply says, this is a heavy, massive particle in a moving meson, then it will also move. And then on top of that trivial motion, which I can eliminate by going to the rest frame, on top of that, there is a little, in German we say Zitterbewegung. So this thing is not exactly at rest because it interacts a little bit, a tiny little bit with the surroundings, okay? And that's described by this residual momentum K. So basically we want all the interesting physics is in this part of the momentum. The rest is just trivial physics. So when we construct HQET, we'll basically construct it in a sequence of steps. So I take the spinor field for a heavy quark, Dirac spinor, psi of x. I want to describe the physics of this residual momentum, so I can simply remove this trivial piece by pulling out a phase factor here. Let me just pull this out. This describes an initial state particle with momentum equal to mq times v. That's the trivial part. Let me just pull it out. And now I'd introduce a new field. And the new field is split up into two components. And the names for these components are little h and capital H with the subscript v. V is the 4 velocity, this guy. And I define these fields, little h and capital H, by the following strange-looking constraints, namely v slash acting on little h is supposed to be plus little h, and v slash acting on capital H is supposed to be minus capital H. And you look at this and you say, well, that's weird. Why would I do that? That's so strange. Yes, it is at this point, but with these definitions, basically, it's not difficult to see that you can solve for these as follows. So, you know, you have to correct for the phase factor. And now this is simply 1 plus v slash over 2 times psi of q. And the second field, same phase factor, e to the I m v dot x, 1 minus v slash over 2 psi of q. And you see that if you add these two, 1 plus v slash over 2 plus 1 minus v slash over 2 simply adds to 1. You get the phase factor times psi, and then the phase factor is removed by this phase factor, and you get psi back. So this is clearly, I mean, this is a split up that is consistent. It's simply splitting this 4-component field up into two other 4-component fields, but actually in the rest frame, you evaluate these operators here in the rest frame, you will find that they simply project out the upper 2 and the lower 2 components of the spinor. So basically, I'm decomposing a 4-component spinor into two 2-component spinors. Okay. Yeah. So we'll do this construction for each of them separately. And then the high momentum exchange that you describe is, for instance, a weak interaction where a B quark, let's say, decays to a charm quark. And that's done by a W boson. It's a very heavy particle. It can do this high energy exchange, but we would then add this weak interaction operator as an external source. So the construction I'm going to discuss here is for a single heavy quark, but for each heavy quark, you can do the same construction. A good point, thank you. Okay, so, for the time being, just accept this. This is an identity, just accept this. And now we plug this in, the heavy quark part of the standard model Lagrangian. So just the Dirac Lagrangian psi q I d slash minus mq psi. We're going to plug in this, this definition. So the psi bar, obviously, I will get h bar v little h plus capital H bar. I'll get the phase factor. For the conjugate field, the sign changes, so I get a plus sign. The Dirac operator, d slash minus m. The phase factor, e to the minus I, m v dot x, and little h plus capital H. Okay, very easy. And now you see we would like to pull this phase through to cancel these two phases. But of course, there's going to be an extra term where the derivative acts on this x here. We have to be careful about. But if we do this carefully, what do we find? We find h bar, little h bar plus capital H bar. And now, once I pull the phase through, it cancels this. So this operator now becomes I d slash minus mq, but now an extra term where the derivative acts on the phase here. This extra term is an I times a minus I makes a plus m times v slash. And then little hv plus capital HV. Is this still okay? Yeah, you see what happened there? Okay, and now we simply split this up into 4 terms, and we use these properties. That whenever I have a v slash acting on little h, it stays little h. Whenever I have a v slash acting on capital H, there's a minus sign. So there's going to be a term with 2 little h's. For the term with 2 little h's, this v slash acts on little h, that gives a plus sign. Then I have plus m here, minus m there, so these 2 terms cancel. So then only d slash remains. Yeah, you see the cancellation between these 2 terms when they act here? It's simply this condition. For the capital H, similar situation. Except that for the capital H, v slash acting on capital H gives minus capital H. So I get minus m from the mass term and minus m from here, x minus 2m. And then I have the mixed terms. And in the mixed terms, let me write them down. In the mixed terms, I just find that the mass term cancels out again. So let's look at the second mixed term, for example. The v slash acts on this little h and produces +1, and then the mass term cancels. And then I end up with this term, and likewise for that. Okay, so actually, honestly, not much has happened. This is not so dissimilar from the original Dirac-Lagrange, but nevertheless, it's a little bit interesting because if you look at the term with the little h alone, there is no mass term. So this term by itself would look like a massless fermion. Okay? Whereas this term by itself would look like a massive fermion with twice the mass of the original heavy quark. And then there are these terms which mix up the two. And the whole thing together is, of course, completely equivalent to this guy. So it just describes an ordinary Dirac fermion, but in a somewhat interesting structure now. So now I can simplify the Dirac structures. And maybe let me be a bit fast here. So let's look at the first term. So remember, this little h contains this 1 plus v slash, we call this a projection operator. And here I have a little h on either side. So if I have a 1 plus v slash from the left and a 1 plus v slash from the right, and I have a slash object in between, so something that has a single gamma matrix, okay? I can simplify this gamma matrix in between these two projection operators contained by these fields. As follows, I can commute this gamma all the way to the left. Then I need to pull it through v slash. That gives the sign change. And then, of course, I have to correct for the commutator term. So then I get an anti-commutator of v slash gamma mu over 2 times 1 plus v slash over 2. Here, I get 1 minus v squared, but v squared is equal to 1. So this product of different projectors yields 0. And here I have the anti-commutator of v slash with gamma mu, which is twice v mu divided by 2. So this is simply v mu, the 4 velocity. And so you see that I can also write this as 1 plus v slash over 2 v mu times 1 plus v slash over 2. I use the fact that, sorry, I should have defined this here. I define p plus minus as 1 plus v slash or 1 minus v slash over 2. And it's easy to show that p plus squared is p plus, p minus squared is p minus, p plus minus p minus plus is 0, and p plus plus p minus is 1. So, which means these are really two projection operators. Project the upper and lower components of the spinor. And that equation tells me that between two plus projectors, gamma mu can be replaced by v mu. I get a similar relation that between two minus projectors, gamma mu can be replaced by minus v mu. And I have a third relation that if I have a plus projector and the minus projector and gamma mu in between, what I do then is I split up this gamma mu into a piece proportional to v mu and a piece orthogonal to v mu. So let me write it like this. So gamma mu perp here is defined such that if I multiply it with V mu, I get 0. Okay, so you see if I multiply this with V mu, I get V slash. If I multiply this with V mu, I get V slash. So if I multiply this with V mu, I get 0 by definition. So perp here means perpendicular to the velocity. And then you see that this first term vanishes because if you act with this V slash to the left, you get +1. If you act to the right, you get -1. A quantity that at the same time is plus and minus itself is 0. And then only the perp component remains. Okay. So now our Dirac-Lagrangian simplifies in the following form. From here, so instead of d slash with this rule, instead of d slash, I get v dot d. So I get rid of Dirac matrices and simply get the product of the velocity vector into this derivative. For the second term, d slash with this relation becomes minus I v dot d minus 2m and for the mixed term, only the perp component survives, basically. So for the mixed term, we have little h, and now only the perp part of the derivative. And likewise in this. Okay, so basically, you can still ask the question, where is this all going? But two things happen. First of all, the field little h doesn't have a mass term. That will turn out to be important. And we got rid of Dirac structures, except for the last term here, where the perp components of Dirac matrices still survive. And that will also become important later on. Now, Anish told you, or is going to tell you, that of course in field theory we always have the freedom to do field redefinitions. It's not unique which field in a Lagrangian describes a particular particle. All you need is a field that has a certain overlap with a certain physical state. As long as a field has a non-vanishing overlap with a certain physical state, you can use it as an interpolating field for that particle in the fast integral. And then you can change variables in the functional integral as you like, which means you can redefine fields and they still describe the same physics. So here in the Dirac-Lagrangian, psi is the field that describes the heavy quark. I'm now going to use the field little h of V to describe the heavy quark. Which means I will integrate over the field capital H. Why is that reasonable? It's reasonable because you see that somehow, the fact that this is massless means that little h somehow describes the fluctuation around an on-shell heavy quark state, whereas this component of the field has a double the original heavy quark mass. So in a way, this describes fluctuations which cost a lot of energy, which costs 2 mq energy, which corresponds to QQ bar fluctuations in the vacuum that you produce a pair of heavy particle and antiparticle, okay? And that's a quantum fluctuation which is clearly not present in the low energy effective theory because I don't have that large energy. So it's reasonable to integrate this guy out. And integrating out really means that in the functional integral, we have an integral over little h and over capital H, and we have e to the I e for x and the Lagrangian, which in particular contains this heavy quark Lagrangian, and we simply perform this integral. So we perform this integral, and we don't integrate over the little h field. And then the result we call e to the I e for x L effective of x. And this is a simple integral because this Lagrangian is quadratic in fields, so it's a Gaussian path integral. This is the one path integral that you should know how to do. It's a Gaussian integral. And the answer is that LQ effective is equal to little h I v dot d little h plus h I d slash perp, yet now the inverse of 2mq plus I v dot d. It's the inverse of this differential operator. I d perp little h. So you recognize all the pieces. The first term is the same as here. This thing which stands between the two heavy fields goes in the denominator, sits here. And then the thing that brings you from little h to capital H and back, it's the perp derivative. You see it here and there. So essentially the second term describes, you start with little h, you go to the big H, you do the propagator of the big H, and you go back to the little h. That's essentially what the second term describes, but this is simply the result of this functional integral. And there's a functional determinant which is irrelevant, which is just a constant in this case. Okay. That's a good point to finish the first lecture, also because I ran out of space. But maybe after the break, what we'll discuss is that I'll show you an alternative way of getting the same result, and then of course we will work with this result. But before we go to the break, let me just say something that's very nice here. So this field little h, because of this phase redefinition, which we applied, these fields all just carry in momentum space this residual momentum, which we assume to be soft. So you see that this is a soft derivative here, because this field carries the residual momentum. So let me add an index S here. This is a soft derivative, a soft gluon interaction or a soft derivative. Likewise here, all of these fields are soft derivative. And you see that the first term is this, it's very simple, no mass term, and also no Dirac matrix, right? So we got rid of two of the essential features of the Dirac Lagrangian. The Dirac Lagrangian has this big fat mass here, and the mass is very different for the top quark or the bottom quark or the charm quark. Here the mass has completely disappeared. So this is a universal way of describing fluctuations around the mass shell for a heavy quark, which is mass independent. And the Dirac structure has disappeared. That will be a spin symmetry that we're going to mention later. And then there's a more complicated term, but the more complicated term is inversely proportional to 1 over 2m plus some soft derivative, okay? So you see that in the m to infinity limit, this second term is actually going to disappear. And then we are left with this very simple effective Lagrangian, which now is really much simpler than the original Lagrangian because it doesn't have the mass and it doesn't have the Dirac structure anymore. Okay, so basically this is the first term there is the effective Lagrangian of heavy quark effective theory, and the second term we'll see is a set of corrections in inverse powers of the quark mass correcting this first term. All right, so if I understand correctly, we have half an hour break now, a tea break, or we can also have questions now. Yes, sure, please, go ahead. It's a two-component fermion. It's not a Weil fermion in the sense of, you know, left-handed and right-handed chiralities. But it's essentially a two-component fermion. Yeah, we don't call it Weil fermion. While usually we think of chiral fermions in the standard model, right? But it's something like a chiral fermion, something like a Weil fermion, yeah. I mean, it's still a four-component object. It's just that if you go to the rest frame, you will find that it only has the two upper components. And this is true if you use the Peskin-Schroeder basis for the Dirac matrices. Of course, it's a basis-dependent statement, but in that basis, this would be the upper two components. But if you go to a frame where the particle moves, it still has four components, but they're not all independent. Two of them are linearly independent. And you can think of this as the, you know, this is the two components which survive in the infinite mass limit, whereas the other two components go to zero in that limit. And then the two components is really just a Pauli spinner with spin up and spin down, basically. So it's more like a Pauli spinner rather than a Weil spinner. This is the definition of perp. So perp, if I have a four vector object with a perp on it, it means orthogonal on V. So if you start from here, this gamma mu perp really, let me do this for any object. Let me call a vector B mu perp is defined to be the original vector minus V mu V dot B. That's the definition of what I mean by perp. And that definition is such that this implies that V dot B perp is zero, as you can directly check. So basically, a perp 4 object in this context means take the original 4 vector and subtract the component in the direction of V. In the rest frame, this would leave the spatial components left, and the time component is put to 0, basically. So you can think of these perp objects as the spatial components in the rest frame. And I will confuse you starting tomorrow, because in SCET, there's also going to be a perp, and it's a slightly differently defined perp. But there's no. I just looked away and suddenly I found you replaced D with DS. Yes. Yeah. I replaced D with the DS. Yeah, don't be shocked. I will come back to that. So what I mean here is this is just this is a soft derivative, basically, because yes. So by construction here, the little H field only contains the residual part of the momentum due to the soft interactions, but it also means that the hard gluons are integrated out. I will come back to that in the second lecture. Exactly. But of course, this is not a deep thing I do here. I just pull out a phase from a quantum field. I just make sure that the so-defined fields only carry what I call K. The fact that K is a small momentum, I told you it should be like that, but that's somehow physical input that I'm adding there, right? I mean, the field can have any momentum, of course. But I'm just saying, if you consider this situation a heavy quark softly interacting with some light quarks and gluons, then this is a soft fluctuation, and then this will be the case. If I consider this heavy quark and I bombard it with whatever, a cosmic ray or whatever, and change its momentum by a huge amount, this would not be an appropriate construction. Yes. Oh, yes, forget the photon, but it does. Of course. Yeah, I mean, we are in the low energy phase of QCD, so it contains gluons and photons. By assumption. Yeah, okay, so here I'm really just looking, so here the situation is QCD only, a single heavy meson with a heavy quark, and now, you know, how do I describe the physics in that bound state? Now the comment was very well taken. I think we're in the discussion part, so maybe I can I go outside the line? Not really, no, because I will be off the, I'll put it here. So your point is, of course, extremely well taken. I can consider the situation where, let's say I have a B quark, and now some weak interaction process here, and then this guy becomes a charm quark. And now maybe this has some velocity v, and this has some velocity v prime, and they're different, okay? And this is a W boson. Now, of course, this W boson is a violent source, if you want. This guy is 100 GeV, it's much heavier than even my quark masses. And then this guy can do whatever, muon and a neutrino. So, you know, here now I have a weak interaction source that suddenly, out of the blue, takes my B quark with one velocity and replaces it by a charm quark with another velocity. And that can happen, absolutely. But nevertheless, if I consider the situation where this B quark is bound in some B meson, and now here somehow this C quark is bound in some D meson, you know, the inner structure of these bound states is still described by this Lagrangian. So in order to deal with the situation, you have your heavy quark Lagrangian for the first meson, for the second meson. They can have different flavors or different velocities, no problem. The flavor has disappeared here, except for these correction terms, and the velocity is here as a label on the fields. And now we would add this weak interaction as a perturbation to this theory. And we would say, well, now study the weak transition of a B meson to a D meson mediated by such a weak current, V minus A coupling of a W boson. And that's exactly what one does. That's exactly what one does. You describe both of these states in heavy quark effective theory, and then this transition is what we would call a form factor, a weak form factor. Yeah. Well, and actually, you know, really the moment, I mean, if you, so let's say you look at the momentum transfer here, let's say the Q square of this W boson. Then of course, what you find is that, let's say, the B quark momentum minus the charm quark momentum, that's equal to the Q of the W boson. And I can still write this as mb times velocity v plus k mu, and now minus for the charm quark mc times v prime plus k prime mu. Okay, and this has a piece mbv minus mc v prime. And this can be big, as you say, the velocities can now be very different, the masses are very different, this is 5 GeV, this is 1.5 GeV, so this can be big, many GeV, right? But then the difference of the two residual momenta, this is lambda QCD, this is lambda Q, this is still lambda QCD, so this is still a soft momentum. So it works, it's not a contradiction. I mean, the physics inside these mesons is still soft. You know, these, in a way, these antiquarks and gluons, well, they feel that from one rest frame, they go to another frame where they start moving a little bit, okay? But it's not that they get many GeV momentum transfer. They get soft momentum transfer, but they need to start moving. And this transition from not moving to moving gives rise to a form factor suppression. And that's described by a function. This form factor has a name. It's called the Isco-Weiss function, and it's a function of the change of velocity, but irrespective of the quark masses, because the quark masses don't appear in this theory anymore. No, you can have as many quarks and gluons inside the hadrons as you like, but only a single heavy quark. See, yes, that's true. So if you want to have bound states of like a B sub C meson with two heavy quarks, or a upsilon or germanium, it's a somewhat different construction. The construction starts in the very same way, but as I said, the power counting is different and it's called NRQCD. If you read a paper on NRQCD, you will say, well, this actually looks very much like what you told us about heavy quark effective theory, but it's not quite true because the systematics is a bit different. And the reason is that the size of such a, so here I told you that the size of this is inverse lambda QCD. If you have a bound state of two heavy quarks, then actually the size is of order alpha over MQ. It's much more compact. And then the expansion is not in lambda over, the expansion is not in lambda over lambda QCD over MQ. The expansion then is in powers of alpha and in powers of the relative velocity between the two quarks, which is also of order alpha. So it's more like a perturbative expansion. Maybe one more question since she just, and then ask your question and then we break. Yes, so in some sense, these are because of the mass term here, or you can also, if you interpret this as a propagator, you know, just think the derivative will give a momentum. So what you have here is like a propagator 2m plus v dot k. Essentially, it's a, you know, it's a fluctuation costing twice the mass of a heavy quark. So what this actually corresponds to is that you have, let's say, a soft gluon and it splits up into a quark-antiquark pair, but a heavy quark-antiquark pair. And then these two propagate for a little bit and decay again. And this is exactly the type of fluctuations that disappear in the infinite mass limit because they cost a very large amount of energy. So in some sense, it's a smart, you know, a posteriori, you see that this was a smart split up of the fields because, you know, for an on-shell particle, p slash psi is equal to m psi, which is the same as to say that v slash on the spinner is equal to the spinner. So this is in a way an on-shell heavy quark, and this is not because of this minus on-shell. So this would be the particle-antiparticle fluctuation. Tuhin, do I clean the board or somebody will clean the board? Okay. You had more questions, no?